Greetings and welcome to Week 3, Unit 1. It is on projects and internship. Till now, we were trying to understand various curricular components of any curriculum. As we have seen, curriculum has several components like humanities and social sciences, basic sciences, engineering sciences, professional core, professional electives, then you have projects, then you have open electives, and so on. So now we will look at, having seen professional core and professional electives in the last unit, we will now look at the design projects and internship. That is the component. Now there are 4 activities in the suggested curricular design that require product or problem orientation. One is to introduce a course on engineering product design in the first year itself, and 1 or 2 mini projects. Then you have a major project in the 7th and 8th semesters, and then you have internship. And these are really, all these activities will give true engineering experience to students, and if they do them right, it will significantly enhance the placement opportunities. Now, one of the things that is practiced in most of the courses is a sequential learning, that you learn the basics or basic concepts and try to solve some limited type of problems, and then put it all together in the final year in trying to solve an engineering problem through a project. Now, what has been found in the last few decades, it is not necessary that to experience engineering itself, you don't have to go through the sequential process. One of the best examples for this is Purdue University. They have been running a course called Engineering Product Design. It is offered in the first year. All engineering students from all branches participate in that, and they have excellent laboratory and faculty for that. And physically I've seen the facility, how they conduct that, and actually doing such a thing right in the first semester will give excitement to all the new students. If you kind of load them with all theoretical courses saying that they are important concepts that they have to learn, then the excitement of doing engineering is lost. Whereas if they experience what engineering is through a course like this, then they will feel excited that they can solve problems, they can build things, and so on. So one of the strong suggestions in our new design of curriculum is to introduce engineering product design course. We have attempted this in Gujarat state a few years ago. It was quite well taken even by the faculty. Let us take a look at it. And of course, it takes quite some time for the faculty and the departments to adjust to this kind of activity, but it is worth it. In the beginning, you can keep it somewhat simple, and as you understand the whole process better, you can make it much more exciting in the following years. Now, the course is to be offered in the first year to enable students to experience what engineering is. It requires focus on design thinking, empathy, and prototyping rather than complex mathematical modeling. That is, you don't have to go through what you call so-called basic concepts from physics or basic sciences or engineering sciences to attempt to solve a problem. But first thing is, the purpose is to understand what is the problem and how you can think of producing a solution without really understanding all the basic sciences part in that. In USA, It is called cornerstone project. Because they have what is called uh, capstone project, where we call it fourth year project. They call it capstone, but it is called cornerstone project when you do it in the first year. It gives experience to students to work as groups in creating their own solution or product that meets some need of the society. And whenever you look at a problem that meets the need of a society, it doesn't belong to a single discipline. Generally, it will always be multidisciplinary issue. There will be people issues, there will be mechanical engineering issues, there can be civil engineering issues, there can be electrical issues, and so on. For example, an ECE student can design a mechanical gadget because you are in the first year, you have not specialized in anything. You can say some mechanical thing will have to be made. You say, how do you go about doing it? That's it. A civil student can design a smart sensor housing. It can be anything. These are just examples. It is going to be skill based. It moves away from rote learning to learning by doing. You try something. If it doesn't work, you try something else like that. And it's also what you call multiple entry, multiple exit friendly, because that is the requirement of NEP 2020. If a student exits after first year, they carry the design mindset and basic prototyping skills useful in any industry. That is, based on this experience alone, they can get a job. They can provide that kind of assistance even with first year type of training. And here we suggest it is to be offered as a 3-credit course. If you master the mechanisms, if you master the process part of it, how to do it in an organized way, maybe at a future date you can reduce it to 1:0:1 or simply 0:0:2. Either way you can convert that. So that is the engineering product design course. These are the features of that. Now, let's say if you are offering such a course, as we have already stated in the earlier programs, that a course is to be described in terms of course outcomes. And if you look at this, a quick look at this, you can see that the various Bloom's levels are, other than understand and apply, you can address higher cognitive levels of Bloom and also variety of knowledge categories. Let us look at this is once again, this is not the only way to define this course. Okay. Identify unmet social and technical needs by conducting a stakeholder interviews and empathy mapping within a given local context. That means the students are required to somehow interact with somebody. They first form groups, maybe 3 to 4 students in a batch, and together they discuss, talk to potential customers, and through the interviews find out what their local requirement is. It can be simple because the whole purpose of this course is to give experience in engineering itself. And having talked to them, having collected the information from the local context, you define a concise problem statement and design specifications by analyzing user requirements and existing market constraints. Okay, like you can look at your day-to-day requirements and say that how do I save time, let's say in procuring my groceries for the week, something like that. And then you talk to people how they go about doing it and see whether you can develop even an app for that. It should be possible so that the time spent in getting there, maybe people are already doing that kind of thing now with so many apps available on free. They can take care of their procurement requirements. But you may also want to add additional features, which is the best place, which is a high quality place, like that. And then CO3, generate multiple creative conceptual solutions for a defined problem using ideation techniques like brainstorming, Scamper, or mind mapping. Using any of those tools, you can create multiple conceptual solutions. One of the things that you need to learn, never focus on one particular solution and then try to spend a lot of your time in justifying why it is the best. First, get multiple solutions from different members of the group, and then work out a mechanism by which you will actually identify how do I select the best one out of that. What are the criteria that you will use to select the best one out of that? Okay, so generate multiple solutions, and then develop a low fidelity physical and digital prototype of a selected concept using basic fabrication tools. These, because you are not specialized in anything, the only thing that you can do, if you have access to 3D printing, these days it is available everywhere, or you can work with cardboards or some modeling software, depending on your interest. You can use any of them to develop a low fidelity physical or digital prototype. That means it doesn't exactly meet some of the physical requirements. That's why you call it low fidelity, but at least it's functional. You can show that whatever I'm developing is functional. And then next one is evaluate the design product based on criteria of sustainability, cost effectiveness, ergonomics, and ethical implications. Now you should spend enough time to focus on whatever solution you have produced together. First, you produce different conceptual solutions, then you went through a process of selecting the one, and then you developed a prototype, and then you evaluate that prototype against the criteria of sustainability. Sustainability will include the kind of materials and energy that you spend in creating that, and when you retire the product, what is involved in that. Okay, how sustainable the product is, and then how cost effective it is, how convenient. Ergonomics means how convenient it is for people to use, and are there any ethical implications if you are using, let us say, some toxic chemicals for something to work, or it has very sharp edges which can hurt the user. You find out whatever that ethical implications are and evaluate and come with a solution. And then you communicate the design journey and product features through a technical report and a formal multimedia presentation. Then you work on creating a report. It doesn't have to be too elaborate, but you will get experience of how to report. And can you create a small multimedia presentation that will constitute really the suggested course. So if you quickly go through each one, introduction to design thinking means difference between engineering design and artistic design. The artistic design generally goes through only one, you're only making one type of, you're producing only one type, one unit. Whereas engineering design would mean that can you manufacture them in multiple numbers. And then you can go through, the CO1 will make you go through this 5-stage design thinking process. That is, you empathize with the user's needs, then define the product, ideate, prototype, and test. We have gone through all of them. That is the design thinking process. And you can also give some case studies like iconic Indian product designs. You take Jaipur foot, low-cost water filters. Some of them have been designed. You can use those case studies to explain what product design is. Okay, you can look at all the details by taking examples of this. Then CO2 is problem identification and specification. Techniques for user research, it is observation and interviewing. Then creating user personas. That is, you consider how does the user interact with this particular product, how convenient it is. That means only you are looking at your potential users only with regard to your proposed product. Okay, then translating customer voice into technical specifications. For example, we have done some time ago a project with our students where there is an ice cream cart that people go, you have, right? They come to near your house and ring a bell and see whether any children are interested in buying the ice cream. So we created even a competition among our students where how can they design a good ice cream cart? What are all the features that need to be built into that? First of all, where is it available? How does it come to that? How does it keep it cool? How easy it is to take it around the streets and so on. Some of them you may be able to solve intuitively, but you do it a little more systematic manner. Then CO3 is ideation and conceptual design. So there are two stages actually, divergent versus convergent thinking. Divergent means you just keep on producing ideas, different type of solutions. Functionally they should work. Some of them may be not cost effective or difficult to manufacture, whatever it is, but you first produce ideas. And then convergent means from those alternatives, you are now converging to one of the solutions together. Okay, this is done as a group activity. Okay. CO4, prototyping and realization, the role of what you call fail fast and fail often. That is, don't take too much time to produce one solution. You try to quickly come to one way of doing it. If it fails, again you take another one. You start with another idea, how to make that. Actually, you would have seen many YouTube videos where very complicated products people have tried and where they failed and how they modified. There are plenty of them are available, and you can direct your students to look at some of those videos and how they finally come up with the solution. Types of prototype: proof of concept, form study, visual model. Okay, and some tools are available depending on what is accessible to you. You can do it in your workshop or get it done outside, or it can be purely digital simulation. Then you go through CO5 and CO6, which is product evaluation and ethics, and design for environment and sustainability, basics of intellectual property rights and patents, effective storytelling and technical documentation for products. Actually, this will be a wonderful experience for the first year students. They feel really excited about engineering if they go through a course like this. And that is what, as faculty, you should put them on. They should feel excited about engineering itself, not as a set of courses where some mathematics is there and they have to somehow write the written exam. So here, the evaluation is not based on writing a written exam, but based on the quality of what the students have done, whether they came with a good concept, whether they were able to quickly solve, how they traveled through that, how many times they failed, how many times they were able to correct themselves, and so on. So it has plenty of scope for experience engineering. So we strongly recommend this cornerstone project. Some of the US universities are trying to introduce this, but it requires it requires a lot of preparation on the part of the department to make this successful. It is not like a single theoretical course which you assign to one faculty. As a group of faculty of the department will have to produce this, or different departments can come together and create a mechanism by which all the engineering students can experience that. It depends on your context. For example, many private universities have a very large number of students in the IT disciplines, almost 1,000 people. To them, if you want to put them onto a physical product design, they may or may not get excited. It depends on how you want to group your students and what kind of thing they do. But whether it is IT or civil engineering or anything, they should experience engineering. That is what it is. Now comes the another set of experience called mini projects. We suggested in the proposed curriculum 2 mini projects, one done in 4th semester, the other done in 6th semester. That will be followed by major project in the 7th and 8th semester. And these mini projects are what you call gives experience to students in to attempt to solve ill-defined problems. Okay, this can be done through mini projects of 2 credits in 2nd and 3rd years of the program. The instruction can be through problem-based learning, because the problem-based learning is one of the recent methods of instruction which will make student really experience various facets of problem solving. These projects can be offered as one student or as 2 to 3 student projects also. Generally what happens, this is my view, every branch of engineering has multiple streams. Okay, like ECE, if you take, it is electronics and communication. If you take EEE, electronics and electrical. And if you take mechanical, they will have design, manufacture and thermal engineering. So what can happen is, if the student wants to, let us say in mechanical engineering, specialize in design, he can experience the other through mini projects, the other streams through these mini projects. Like thermal or manufacturing, they can experience through a 2 credit type of project. And the main 4th year project they will do it in their area of interest, like design. Okay. And in this, rubrics can be designed to evaluate the student performance. Because once again, you don't have a written exam for this, but what are the rubrics that you will use to evaluate the student project? And these rubrics should be communicated to the students right at the beginning of the project. So that will make sure that the students do not take their own intuitive paths in different directions. Because in the end, we need to generate some knowledge by which both the faculty and the department will greatly gain. Now, the problem-based approach to instruction, this was looked at in a companion course, but to repeat a little bit, the term problem-based approach is being used in several broad senses these days. Sometimes the term is used interchangeably with terms like inquiry-based approach, active learning approach, experiential approach, and so on. We call it PBL, problem-based learning. In undergraduate engineering is a student-centered instructional strategy where students learn a subject through the experience of solving an open-ended, ill-structured problem. Unlike the traditional methods that that teach theory first and application later, PBL uses the problem to drive the learning. Because while solving the problem, you need to understand some theory, then you will go and try to learn that on your own. Here, obviously, this process is not very efficient in terms of time. So, it is generally PBL values effectiveness over efficiency. Okay, learning should be both effective and efficient, but what happens, PBL, you can certainly do it through a 2-credit project like this. It values effectiveness or efficiency in the sense that you have time. You can't put this into a theoretical course and put a lot of emphasis on PBL type of learning because students don't have that kind of time. Many people have attempted to try to incorporate PBL into all courses. Then they had phenomenal difficulty in managing that kind of thing. Just to give a little background on problem-based approach to instruction, historically PBI, the problem-based instruction, was developed in the context of medical education, McMaster University in 1969 in Canada. One good definition of PBI is a progressive, active learning, learner-centered approach where unstructured problems are used as a starting point and anchor for the learning process. That is, actually, if you look at all the phrases in this, it completely explains what the purpose is. It's quite popular in medical education and allied areas, but is being used more and more in several other domains as well. So, first feature is ill-structured problem. In engineering PBL, because you have to redefine this in various contexts. If you are taking let us say, literature as a program, then PBL will be of a different nature. In engineering PBL, the problem is not simple textbook exercise with a single right answer. It is ill-structured, meaning it is first complex. It mimics real-world engineering challenges. Let's say I'm just giving an example. Design a sustainable water filtration system for a village where you have small number of residents, maybe few hundred, and depending on where the water source is available, what kind of sustainable water filtration system do you want to use? It is not that this problem is not solved, but depending on the context, one solution doesn't fit all. Okay? Then generally you have missing information. Students don't have all the required data. They must identify what they know and what they need to find out. Okay? Multiple solutions. There are many valid ways to solve the problem, forcing students to justify their technical choice. This is already, as we have explained in the previous thing, engineering product design course. This is, you have to produce multiple solutions and then try to find out what is the best one that you can pick from there. And also, there is a shift in teacher's role. A teacher will only facilitate the process rather than lecture. Teacher is not going to tell them solve like this. You understand these concepts, apply this mathematics and solve that. That he is not going to say. Teachers will not give direct answers. They provide scaffolding, guiding students with probing questions to help them discover engineering principles on their own. They monitor group dynamics to ensure all students are contributing. That is the role of the facilitator. Okay. Again, there is a lot of dynamics associated with that. How many faculty will participate? Let us say in a particular branch, you have 120 students. And even if you have 3 students per batch, then you still are talking about 40 different projects. Do you repeat the projects, or you want to address 40 different projects? 40 different projects cannot be addressed by one or two faculty members. They have to be, so it requires a lot of discussion among the department faculty to put this in place and to make it really useful. And in the end, you are producing usable knowledge. And then another feature of PBL is student-centered autonomy. Students take full responsibility for their learning. They must define the learning objectives required to solve the problem, conduct independent research, that is self-directed learning, decide how to allocate tasks within their team. They do all that by themselves. If you want, you can generate some kind of an app for that, so that the communication among the teacher between the teacher who is facilitating and among the students, you can make it simple by creating an app for this. It has been done also. Then collaborative teams. Engineering is a team sport, and PBL reflects this. Students work in small groups, develop professional skills, soft skills such as conflict resolution, communication, and project management. When 3 or 4 people are working together, obviously no two people will exactly have identical ideas. So you must learn how do we really resolve the if there are any conflicts, and then how do people communicate with one another, and how do you manage the project, because they finally, with respect to the project, all the participants should come onto the same page, and that is what you are required to do when you actually join an organization. And also you peer teach one another as they gather different pieces of technical information. So put it all together, each one will explain to the other members of the group what they have procured, whether they are compatible with their project objectives, and so on. And then it is an iterative process. It follows specific cycle that mirrors engineering design process. So first thing is encounter the problem. Where do you start? For example, you take the water filtering. Where do you start? Do you look at the population, or do you look at where the source of water is, or you start with the technology? What do you start with? So you have to identify the hook from which you really start looking at the problem. Internal analysis means what do we know? What are our hypotheses? Identify learning gaps. What physics, maths, material science concepts are we missing? Self-directed study. Students go to the library or lab to learn the missing concepts. Now these days you don't have to go to the library. You have plenty of information on the internet, and these days you have even help of AI in locating the information. Apply the new knowledge to create prototype or solution. Then you reflect. This is one of the important features of this kind of learning. That is, having done something, you reflect on what you have done. Evaluate the solution and the learning process. For example, you might have committed some errors in the way you are looking at the problem. And if you are able to sit together and discuss and note down that yes, this is the point where we should have done it differently, that constitutes a great learning process. Okay. Then you have integration of disciplines, because most of the problems are do not belong to one particular branch. They will have mechanical, electrical, you have electronics, there is economics of that, there is the cost of materials, and so on. Then the authentic assessment is not just one written exam. You how well did the student research and collaborate? Peer evaluation. Students rate each other's contributions. Product defense. Students present their solution to a client or a panel of experts uh, in making their technical decisions. So, if you make the assessment authentic and communicate to the students, that will make the students take the maximum advantage of PBL. As you can see, it takes a lot of planning and effort. And what are the advantages for engineering students? Increased retention. Students remember concepts better because they applied them immediately to a problem. Workplace readiness. It bridges the gap between theoretical classroom learning and the high pressure collaborative environment of the engineering industry. Because in industry, you have always timelines, you have cost constraints, and you have to work with several people of different disciplines. You have to interact with customers. All that issues that come from create a high pressure environment, you are already preparing yourself for that. Uh, Actually, a PBI will move students from Bloom's taxonomy from remembering to analyzing and creating. Okay, so your journey is planned towards higher Bloom's levels as well. That is the advantage of engineering. What do you call this problem? Now we come to fourth year projects. Fourth year project called capstone project or senior design in the context of ESA, whereas we have been doing it for several decades, we could just call it final year project here. Is the culminating experience of an undergraduate engineering program. It serves as a bridge between academic environment and professional practice. It is unlike individual course projects. Fourth year project is high stakes. That is, high stakes means it carries more number of credits. In our proposal, it carries anywhere from 8 to 12 credits. Each institute may have a slightly different value for this, but it's still high stakes. And it is also long-term assignment. Generally, people, what they do, they distribute it over 2 semesters. Some part of the project you do it in the 7th semester, and some part of it in the final semester. So you are trying to apply the knowledge that you have gained from different courses over 4 years to a single complex problem. That is the idea. Now, key features of fourth year project is it is real world open ended problems. It is like mini project, but with a lot more scope of this, because it also carries more credits. And then it is a multidisciplinary integration. Students cannot solve fourth year project using just one subject. They must integrate technical knowledge, practical skills, and professional constraints. If a institute want to explore different alternatives, you can also create projects where the final year students come from, the project students come from different branches as well. That kind of thing also can be organized. The language the students speak by the time they come to fourth year will start becoming quite different, because you will be using the terminology related to your discipline. But when you put such people together from different branches, you have to go through some process where you can work together. But if you want to explore that, that is also possible. People have done that in different institutes. And another major feature is professional communication. That is, you need to communicate, you need to write technical reports, you have to make formal presentations. Sometimes you have to create posters, showcase your product, and so on. And consideration of non-technical constraints. like the product should consider safety and public health, ethics, and sustainability. These have to be taken more seriously in a fourth year project than in a mini project, because the amount of time that is made available to fourth year project is large. Okay, and this is where the student shifts from student phase to engineer phase. Okay, this is a psychological shift actually. You just don't listen to lectures and solve some problems or remember something and reproduce, but you're actually producing a solution and sometimes building a product. And again, both formative evaluation and summative evaluation should be in place, because you cannot say, I will look at your project report at the end of the project, but people have to oversee during the project time how whether they are following the right path or not. So formative evaluation also should be there, and for this rubrics are are best for best form of evaluation. Then come the other one, internship. Internship for fourth year engineering students are the final step in transitioning a student from an academic setting to a professional one. At this stage, students have completed most of their core technical coursework, making them capable of contributing to real engineering tasks. And this requires also a lot of planning, a lot of things to be put in place between the department, faculty, students, and the company where the student is required to work. And internship is also becoming an important requirement these days as per the accreditation process. To be effective, internship should not be shadowing experiences. They should be structured as a work integrated learning. Shadowing experience means you follow one senior person in the industry, keep going along with him to see what he is doing and write a report based on that. That is not internship. It is a work integrated learning process. So, this also requires plenty of planning, and it may take 2 or 3 years before everybody feels happy with that. You have to put in that kind of effort to make the internship very effective. Selection and matching, instead of random placement, students should be matched with the companies based on their specialization. Internship agreement, a formal document signed by all three parties that outlines specific learning objectives, safety protocols, and confidentiality requirements. This is where the student starts experiencing real world. Okay, faculty mentorship. Every student should be assigned a faculty supervisor who checks in periodically to ensure the work being done is engineering level and not just administrative. Sometimes companies, for their convenience, may ask you to do simple administrative work and give you a internship certificate. It should be at engineering level, but you have to convince the company that you are not coming in their way and you are only contributing. That's what takes more effort on everybody's part. The company must appoint a professional engineer or a senior lead to mentor the student, providing them with the technical guidance and professional feedback. Because what does the company get out of this? If a senior person is kept there to provide you technical guidance, there must be some return for the amount of time that he is spending, right? And that is where the students must understand and try to see that you value this experience and you really learn from this. So one is project based work, that is the company asks you to solve one particular problem in their context, physically in their place. Our interns should be exposed to industry specific standards. Learning how to apply these real world constraints is a feature cannot be easily replicated in the classroom. So they give you some design that is produced in the company and ask you to see whether it meets the technical standards or not. You have various standards available, both Indian and abroad, like IEEE, ASME, and so on. And you must be able to critique the solution from the point of view of standards. And also, internships also one of the primary ways to attain professional outcomes, that is PO6 to PO11, ethics, environment, sustainability, communication, what you call lifelong learning. All these can be addressed through internship as well. And you also experience documentation and reporting, evaluation of performance versus grades. Again, you are not writing an exam at the end of this. Employers provide a performance appraisal, which is often more valuable for the student's future career than traditional grade. Networking and career integration. Internship generally serves as an extended interview. That's what one should be aware of. A key feature of fourth year internship is a high rate of pre-placement offers, where companies hire the intern before they even graduate. Such things happen. So if the students give right kind of importance and put their effort, you may get the placement offer itself. Okay, these are the 4 types of things that we are talking about. That is first year engineering product design course, mini projects, final year projects, and internships. And this is what really makes the whole engineering program engineering. Otherwise, it will be a set of theoretical courses and you will really find it difficult to get the right kind of placements. In the next unit, we will understand the nature of open electives, which is also one curricular component. And thank you for your attention.